Welcome everyone. In this video lecture, we will think about the common gate MOSFET amplifier and a small signal analysis to determine the input impedance, output impedance and voltage gain. So the circuit for the common gate amplifier is shown here. Here the gate terminal is there, drain and source, and we are giving input voltage, AC input voltage across the source in, and we have given also one DC voltage for biasing to the gate side, that is our VG, and one drain resistance RD is there, VDD supply, and we are taking output across the drain side through a capacitor C as the output voltage V naught. So this one is the common gate amplifier, CG amplifier. So for the determination of input impedance, output impedance and voltage gain, we have to go for the AC analysis. So if we go for the AC analysis, the modified circuit will be like this. Okay, we have to change something. So for the AC analysis, what we will do, we will remove the DC part. Okay, so DC part will be grounded. Okay, so this will be our grounded. Okay, clear. The DC part, DC voltages will be grounded. Okay, okay, and so this voltage will be also grounded. So make it ground. Okay, this DC voltage is grounded. Okay, and the capacitor, okay, the capacitor is also sorted. So okay, so this one is the AC equivalent circuit, AC circuit, we can say the AC circuit we have made for the for CG amplifier. Okay, in case of AC circuit, first we have removed the DC voltages and sorted the capacitor value, and capacitor, the capacitor is sorted. Okay, so this one is our AC circuit, we can say. And in some portion we have to do DC analysis, so one that DC analysis circuit also. For the DC analysis circuit, okay, what we will do for the DC analysis, we have to remove the AC signal. Okay, so this one is our, okay, clear. This should be simply, we can say, for the AC one. Okay, it is connected, it is connected. Okay, and this will be, capacitor will be removed. Okay, so this one is our DC part. Okay, so we can say for the DC analysis, but our prime focus will be for the small signal analysis. In this one is the DC part. Okay, but here our prime focus will be for this circuit. Okay, clear. So first what we will do, we have to think about the why this is our common gate. Okay, common gate, because this gate is common for the input voltage. Okay, so basically what we are doing here, input is applied across the source and gate is common. Input is applied across the source and gate is common, and output is across the drain. Okay, output is across the, you can say, the drain. Okay, and gate is common, so gate is common for input and output. Clear. So this one is our common gate configuration, common gate. Clear. We are taking the, we are giving the input is applied across the source and the gate terminal. We are applying input across the source and gate terminal, and we are taking output across the drain and gate terminal. Okay, I'm writing one line. What we can write here? I'm writing input. I'm writing input is like this. Input is applied across source and get. Okay, and we are taking output across drain and gate. So in both gate is common. So in both we can say gate is common. Okay, so that's why this one is a common gate amplifier. Okay, so now we have to find out the input impedance. Okay, so what we will do, our prime focus will be on this circuit. Okay, so first what we will do, okay, so our prime focus is that we have to use this circuit. Okay, this circuit. So what we will do for the a small signal analysis, as we know, for the transistor part, for transistor, I'm just making the circuit for the transistor. If this one is the, okay, gate, drain and source, okay, the equivalent circuit, AC equivalent circuit will be like this. Should be our gate, drain and source, and this voltage will be VGS, and this current, this one is a current source, GM VGS. Okay, so this one is the transistor. Okay, then the corresponding AC equivalent circuit is like this. Clear? So now we have to use this circuit, and we have to make a AC equivalent circuit. Okay, so what we will do here, we will start the thing. Okay, okay, here we will start the thing. So for the small signal analysis, we have to go for the AC equivalent circuit. Okay, AC analysis. So what we will do, there is a transistor. So for transistor, we are making like this current source. Okay, and this one is our GM VGS, and this one is our VGS, and gate terminal is grounded, so we are making this as a grounded. This one is our gate terminal, and this terminal is our drain terminal, and through this drain one RD is there, that is connected here. Okay, and we are taking this as a output, so this one is our V node, and one source is there. This is one is our source terminal. Okay, so this source, through this source we have the voltage. Okay, so we can make like this, say VI. Okay, so this one is the AC equivalent circuit, AC equivalent circuit for the common gate amplifier. Now AC equivalent circuit is over, or we can write a small signal equivalent circuit. For this one we can write it a small signal AC equivalent circuit. Okay, this one is a small signal AC equivalent circuit. Okay, so now we have to find the input impedance. So first thing that we have to go find, say input impedance. Okay, for the calculation of input impedance, what we will do? This one is Vi, and we are saying some current is flowing like I, some AC current I. Okay, so this II, so this Vi by I will give the Zi input impedance. Okay, Zi is nothing but simply Vi by II, or we can write it Z input impedance as In or In, anything. Okay, Vi by II. Okay, so that we have to find. So for this purpose, and this current is our, say, the AC drain current. That's why I'm writing it ID, a small ID. Okay, so this current is also the drain current, that is our ID. Okay, so now we have to apply Kirchhoff's current law at this point, say source terminal. This one is a source terminal. So what I'm writing, by applying KCL at point S, that is the source terminal, or this S. So this one is voltage source. So and this one is current. Current is coming here. So this one is also ID. Okay. This one is our ID. So total incoming current at this point by applying KCL at point S. Okay. So what we can write, I, the input current from this side, is nothing but simply ID. So ID is nothing but simply I of I, or anything you can write I is minus ID. Okay, clear? And this ID is nothing but simply our minus GMVGS. This ID value, the drain current, is GM times of VGS. This one is your equivalent circuit, so easily we can write II equals to minus GM times of VGS. Okay, now this is over. Now in the next part, if we apply Kirchhoff's voltage law in this loop, in this loop, okay, I'm writing by applying KVL in loop 1. Okay, so what should be the KVL equation? It's very simple. We can write minus VGS get to source voltage minus VI is 0. So what we can write, VI equals to plus Vi equals to minus VGS. Okay, so VGS, or simply we can write VGS is nothing but simply minus Vi. Okay, so VGS value is now Vi. So what we will do, I equals to, we will put the value of VGS, we will put the value of this value in this one, VGS. Okay, I equals to minus GM into minus Vi. Okay, so this should be I equals to plus GMVI. Okay, so the value of Vi by II equals to 1 by GM, that is our, nothing but simply our Z input impedance. Okay, is it clear now? So the input impedance will be 1 by GM. So input impedance for a common source amplifier, sorry, the common gate, not source, common gate amplifier is Z in equals to 1 by GM. Okay, Z in 1 by GM. Okay, in case of what we can say, the common drain, or simply in common source, the input impedance is very high. Okay, but in case of common gate, input impedance is low, and generally it is in the what, ohm range, in ohm. Okay, in ohm, typically it in ohm, and z in ideal value we can say 0. So input impedance of a common gate amplifier is 0 ideally. So one line that I am going to write: in ideal case, common gate amplifier has 0 input impedance. Ideal case, but in general we can say 1 by gm. So this is all about the input impedance. Now we have to go for the what, input impedance is over. Okay, now we will go for the output impedance. Okay, so for the output impedance, what we will do, first I am writing output. Only we have to use the kvl, KCL, then you can easily solve them. Okay, so again, what I am doing, first we have to draw the S equivalent circuit. So once again, I am writing the, drawing the S equivalent circuit for this one. This part is our GM VGS. Okay, and this voltage is our VGS. This one is our grounded, and this one is our AC signal, that is our VI, and this one is our RD. Okay, and we are taking output. Okay, so we have to find the output impedance Z naught. Okay, so for the calculation of Z naught, for the calculation of Z naught, we have to find the Thevenin equivalent resistance looking from the output side. We have to find the Thevenin equivalent resistance looking from the output. Okay, this one is our output side. Okay, Thevenin equivalent resistance looking from the output side. So in this case, what we will do, the AC voltage, we have to make it 0 or grounded. So generally we have to say, we have to make it 0 or grounded. So VI, we have to make it ground. Okay, and VGS, if we have to make it ground. Okay, so this one, okay, I'm just copying this circuit. Okay, for the AC analysis, okay, yeah, this will be grounded. This will be grounded. Okay, so this VGS is nothing but simply 0 volt. Okay, or we can say the current, the dependent current source, that is our, this ID is nothing but simply GMVGS. So this one is a current source. So this current source will be open, or this current source will be open. Current source, dependent current source will be open. So what we can do, we have to remove this one. Okay, so simply what we observe, that the Z naught value in this case is simply our RD value. Okay, so this one is the output impedance. Yes or no? Okay, so output impedance is very easy to find. Okay, so output impedance is over. Now we have to go for the voltage gain. Okay, voltage gain calculation. Okay, so for the voltage gain calculation, we again we have to draw the S equivalent circuit. Okay, so this time we will remove this chestnut part. Okay, so for the gain, okay, for the gain, what we have to find, the value of AB is V naught by Vi. Okay, and this current we can say simply ID current is flowing. Okay, this current is nothing but simply ID. Okay, so what we can write, here I am writing this voltage is 0 volt and this voltage is output voltage say V naught, and current is flowing like ID, and this value is RD. Okay, so ID value will be, current will be, this will be considered a higher potential 0 minus V naught by RD because the current is flowing from this side. Okay, so the value of V naught equals to minus ID RD, and ID is nothing but simply GM VGS. ID value is nothing but simply GM VGS. Okay, so V naught is now known to us as a function of VGS. Okay, now we have to find out the relationship between VGS and VI. So what we will do, if we apply KVL in this side, okay, KVL in this side, what we can write, minus VGS, and this one is plus of minus VI equals to 0. So VI value is nothing but simply minus VGS. Okay, I am highlighting this one. Vi is nothing but simply VGS, minus VGS, and now this is the expression for this V naught. Okay, so what we will do, we will put the value of VGS, that is our minus Vi. Okay, so one can write simply V naught equals to minus GM, and VGS is minus Vi RD. Okay, here this VGS is minus Vi. Okay, so there we are putting, so V naught equals to GM, all will be in positive. So V naught by Vi equals to GMRD. Okay, so the voltage gain will be GMRD. In other cases, it is minus GMRD, but here the input and output will be in the same phase. So what we can write? Input and output voltage are in same phase. Okay, same phase. Here V naught equals to GM RD times of VI. In other one, in like what we can say, the common what source, in common source in CS configuration, V naught by VI equals to minus GMRD in common source. Okay, but here it is simply GMRD. Okay, so this one is a important one. Okay, so in case of common gate, input and output is in the same phase, and this kind of common gate amplifier is used for the high frequency application, and it is generally used as a impedance matching. Okay, where the antenna, through antenna we are giving the some antenna output is given to the amplifier. So in such cases we have to use this circuit. So this is all about the about this common gate MOSFET amplifier. So this is the circuit, means how to determine the input, output impedance and voltage gain of this common gate MOSFET amplifier. So thank you for watching this video. Thank you.